So there are charges a q, 2q, and a minus 3q placed on the vertices of an equilateral triangle of side A. Find the net potential energy of the system. It will be k into 2q square by A plus k into minus 6q square by A minus k into 3q square by A. So the answer will be minus 7kq square by A joules will be the total potential energy. This is the energy required to put this in the system. What will be the energy required to take it away to infinity? It will be plus 7kq square by A joules. So the opposite of it. That's the first question in the PSCNA paper. The second question. Consider two identical point charges kept at 0 comma 0 and a comma 0, which means that identical means let's keep it as positive. Nowhere between positive and negative electric field can be 0, but the electric field is possible for it to be 0 at some point here. That will be midpoint, you already know. If you can assume this is x and this is a minus x. 1 by 4 pi epsilon naught q by x square. They emanate from positive, they emanate from positive. So then it's going to be opposite direction. Minus 1 by 4 pi epsilon naught q by a minus x the whole square is equal to 0. So x is equal to a minus x and 2x is equal to a, x is equal to a by 2. So at the midpoint, the electric field can be 0. But nowhere between this, the potential can be 0. They'll ask you to justify this. Assume that point P potential can be 0. How is it possible? It will be, this is again x and this is a minus x. What is the potential formula? 1 by 4 pi epsilon q by x plus 1 by 4 pi epsilon naught q by a minus x. This can never be 0 because both of them are positive charge. The magnitude of it can never be 0. Wherever you take it, even outside, so it's never possible. Between two like charges, the potential can never be 0, and that's a justification. Let's go to third question. Two small conducting spheres A and B of radius R1 and R2 have a charge Q1 and Q2. Initially itself they have a charge Q1 and Q2. Now you're connecting it by means of a metal wire. The moment you connect it by means of metal wire, the charges will change to Q1 dash and Q2 dash because the charges tend to flow from higher potential to lower potential until they arrive at a common potential. So the common potential here, but you know, by conservation of charge, capital Q is equal to Q1 plus Q2. And capital Q is also equal to Q1 dash plus Q2 dash. Keep it like this. And you know, common potential should be calculated based on the acquired new charge, the final charge, which is equal to 1 by 4 pi epsilon naught into Q2 dash by R2. So Q1 dash into R2 is equal to Q2 dash into R1. And Q1 dash into R2 is equal to Q2 dash can be written as capital Q minus Q1 dash into R1 from this equation. And so substituting and taking it in, Q1 dash R2 is equal to Q R1 minus Q1 dash R1. And consolidating Q1 dash into R1 plus R2 is equal to Q R1. So Q1 dash is equal to Q R1 by R1 plus R2. So if you want to find Q2 dash, it is total charge minus Q1 dash, which is total charge minus Q R1 by R1 plus R2 from the previous equation. Q can be taken out 1 minus R1 by R1 plus R2. You take LCM, it will be R1 plus R2, R1 plus R2 minus R1. So then it's Q into R2 by R1 plus R2. And this is what is Q2 dash. And they ask you the ratio of Q1 dash by Q2 dash. You know, R1 plus R1 plus R2 in this equation and this equation will get cancelled. Capital Q, you still get R1 by R2. The same as the sum that I gave you in the exam was the ratios of surface charge densities, in which you had the same R1 by R2's ratio. But in that, after connecting by means of a conducting wire, the charge is low and the acquired charge is Q1 and Q2. So I didn't have to do the Q1 dash and Q2 dash. But if the wire is connected later, then the acquired charge will be different. Okay, the charges tend to flow, and this is what it is. So let's go to the next question. The same sum, there's another. Okay, the fourth question. A parallel plate capacitor C1 has a charge Q. Okay, and you know it's been charged to a potential V1. Let's take it like that. So Q is equal to C1 V1. It is being connected with another identical capacitor. Identical but uncharged. The capacitance is still C1, but it is uncharged. The potential is 0. And so then this is not like sharing. The sharing means it's got to be like this. It will become parallel, and means it's like a sphere A is touched by a sphere B. The charge is on A is Q, and this is uncharged. It will become Q by 2 and Q by 2. Remember, it's similar to that. You're connecting by means of a wire, so the charge here will be Q by 2, and here also it will be Q by 2, and that's all. So the final charge on C2 is just Q by 2. That is part number A, and B is three identical capacitors of 3 microfarad are connected in series and parallel. So you have 3 microfarad, let's give it a CCC, connected in series with a battery of V volts, and another with parallel. Other connection is by parallel connection and connected to a potential again of V volts. They're asking for the ratios of their energy. You know that equivalent capacitance here will be C by 3, because 1 by C plus 1 by C plus 1 by C is 3 by C, so C by 3, and the equivalent capacitance here will be 3C. And you know C itself is 3. It's been given here as 3. When you substitute 3 microfarad, we 1 into 10 to the power minus 6 farad. And C itself is 3, so 9 into 10 to the power minus 6 farad. And the energy, therefore, let's be half C V square. Half C in this case is minus 10 equivalent capacitance into V square. And here it's half into C, which is 9 into 10 to the power minus 6 into V square. So the ratios of these two is just divide, half and half will get cancelled. It will be in the ratio 1 is to 9, because V square and 10 to the power minus 6 get cancelled. So answer is 1 is to 9. So let's go to next question. The fifth question. The space between the plates of the parallel plate capacitor is completely filled with two ways. There's one capacitor in here where there's a dielectric constant K. There's another capacitor, the same distance D, but half of this D by 2 is filled with a K1, and half of it is filled with the dielectric constant K2. The moment you see this, no, this is positive terminal, negative terminal, which means you should assume this is positive, negative. Therefore, this will become negative plate. This end will become positive plate. That is when this end can become negative as given. You understand? If this is positive, this entire plate is positive. This is negative, this entire plate, this becomes negative. So you have two capacitors which are like connected in series. That's like a capacitor 1 and that's a capacitor 2 which are connected in series. So in series, okay, let's take the capacitance on this, which is K1 into epsilon naught into A by D by 2. And the capacitance of this is K2 into epsilon naught into A by D by 2. And series, so C1, this is C1 and this is C2. C1, C2 by C1 plus C2. So K1, K2, epsilon naught square A square by D square by 4. C1, C2 into C1 plus C2. Epsilon naught into A by D by 2 is common. C1 plus C2 will have a K1 plus K2. And this epsilon naught square is getting cancelled, A square is getting cancelled, a D is getting cancelled with the D square, and this is getting cancelled with the 2. So thus this 2 goes up in K1, K2, epsilon naught A by K1 plus K2 is all you get. And what is the initial, this one's capacitance is K into epsilon naught into A by D. In the question it's been given that both the capacitors are having the same capacitance. C is equal to C dash. So the similar capacitors, similar capacitance. So then equate this with this. Epsilon naught A will get cancelled. And so by a D, I forgot a D. Okay, so D and D has get cancelled. So K is equal to 2K1, K2 by K1 plus K2. Thus you can find the ratios. Once again, hold on.